Okay, welcome guys. Welcome to the stream. Today we have a very important topic to study. It is GPU and CPU and ASIC and NPU. I need to refresh my screen. It seems it's broken. Okay. Okay, can you hear me? Yeah. If I do like this, it's better, right? Or like this, it's better. Okay, it will be like this. Okay, my screen is working, right? Yep. Xcode. It's morning. It's 6:50 a.m. and today it is Wednesday. Awesome. Yesterday I was working on this guy on Telegram, but let's see if it will if it will run on my phone. I think it will not run, but let's check. It's building. So how it works is that Telegram open source their iOS build their code, so anyone can just clone a fork and then build it. Yeah, it's not straightforward to build. You need to do debug a lot of things, and it may not match with your CPU stuff. But interesting thing is that they don't use Xcode that much. I mean, in order to build, they use a Python code, which is at first looks like very, very crappy, very scary. So let's see if it will work. But today, I don't want to discuss about that stuff. Today, let's talk about. Let's activate the Tmux. It's working, right? Yep, it's working. Oop. Okay. Okay, good. I check my YouTube. Okay. Xcode. Oh. By mistake close my window because there's many things open in my computer and I don't like if it's like that. If this deck is full of items, it's very annoying. Good. It's about grok. Yep, this is where we start. This is a place where we will start. So, there is a company, Rebellion, who produce, it's a startup company, who produce NPU. They have Atom, TM. So we need to really to study about this one. Okay. Software, Rebel Quad, and then Max Server, Max Pod. So this one is recent hardware. It's all fancy stuff. For homogeneous chiplet as system on chip based on UCI. What is UCI? E advanced teraflops flops. I need to compare it actually. It might be just fancy stuffs. Interface 16 gigabits per second, 1 terabyte per second per channel. What is the channel then? Okay, they compare with H200. High performance AI cluster with rack to rack scalability and RDMA network. I know what is it. So hardware is interesting, and it is also not straightforward, not that super simple to build. We can build hardware also, and important thing is that we need to understand. So as far as I know, in order to build any hardware, if you wanted to design new hardware, you need to program, you need to work on Verilog, that kind of language. There is a language, Verilog. So let's go to our folder first, and then we will start it. Actually, Bishik. No, maybe not in actually Bishik. Let's say here vim mkdir make directory our chip. Okay, I see. So my space is almost full, so therefore I am freezing. I need to remove some stuff from my computer. So in that case, I need to go to storage. Because Xcode is super big, super huge, and I don't like that stuff. It's super complicated. Super complicated in the terms that it downloads a lot of stuff which are like just one simulation iOS one device is also very big. It takes a lot of size. Maybe I just clear, if I clear my trash bin, then it would be fine. I don't know. Downloads. Nope, it's not here. It happens, guys. It happens. We need to remove them. Okay. If I don't remove, it would be very difficult for you to follow, because if my screen freezes, then you cannot see real time what's happening, and it creates some kind of frustration for you to follow up. Actually, I have a data set. I mean, I generated one data set 2 days ago, so the data set also is taking some place. So what I can do is that I can just move that all data to my USB-C or no USB. Where is my USB? USB. Okay, just a moment. Okay. Okay, my computer is okay. My USB is there. Then it was where? It is in user, and we go to fun, and then we go to here. Move to trash. Build no. Where is it? Trainer. Get info. Okay, I understand. I understand. Okay, it will take ages to move. It turns out. Okay, I have I have a failure. It's good to close for now the Xcode. Okay. Yeah, again, my computer freezed. Okay, you see that? So you see it now, right? Okay. See our chip. So first of all, we have CPU, right, from long time ago, and in 90s, 80s, in 1980s or 90s, NVIDIA come up with idea of using parallel compute and specifically for parallel computation for what? For gaming, rendering, 3D. And then it turns out no in 2005 or 2008 let's do like this. 2008 CUDA come out, and GPU is very good. It's very good friend for AI training. And then in 2020, or maybe it was before also, there is a new term NPU come out, and then we have a Apple M series chip. Apple A series chip, and then what? Qualcomm. Does they have NPU or AI ideas? Then we have AMD. I'm hearing that AMD is kind of just a losing game, and they are happy to be second place, or they are happy to be loser. I don't know yet, but I know that AMD is not that ambitious company. It supports, no, it has, let's say, it has GPU, it has software, and compatible with storage. Then Snapdragon is a chip name, okay, or a series of chip produced by whom? I mean, who is the owner of the Snapdragon? Is it Qualcomm? Samsung? I don't know. And we have Exynos, maybe like this. Exynos chip from Samsung. And then we have what? We have different types of chip from, we have from Tesla chip. And then we have what in Android? Oh no, okay. We have Intel chips. Does Intel has NPU? The stack of GPU. Writing code in FPGA. For guys who doesn't know what is FPGA, FPGA is a board where you can actually write lowest level of code and actually do a parallel computing. Yes. So if you use FPGA, then you can design for GPU, for NPU, and for CPU also. And you can design ASIC. So ASIC means very, very specific designed chip for one use case. Let's say I have a very good Resident model, Resident 18 model, and I want it to run on cameras, and I want them to run on cameras efficiently and actually really fast, and I don't want to update the model weight. In that case, we just take the model weights and we implement the activations and all these functions of what in Resident we have what convolution operation, and we have linear operation, just dot product, maybe some ReLU stuff or etc. And if we implement this one, and then if we write the model weights hard-coded, weights hard-coded, and then it will work. It will just work then. Hi, think what you are typing. I cannot see on the stream. Okay. Thank you very much. Now maybe clear. What about now? Okay. Welcome, Augustine. Welcome. So that's what I know for now. What information I know, and before that, I actually know that Intel started in 1960s, if I don't mistake, or 1950s, 1960s, and then it is what? Intel chips moving from military moving from military service to commercial usage, for commercial use in 1960s, 1980s. Rise of Japan, memory card production, DRAM, etc. And I know these players, and there are maybe a lot of startups, and I want to really focus on these rebellions. So this is a startup which recently got 250 million, 50 million USD. Recently, just 2 weeks ago maybe. So this, sorry, I think there is something wrong again. Is Veeam won't update. I see. Yes. It's because of my memory. How can I fix that one? Just give me some time. Okay. If it is done, then we go back. Okay. Yesterday, no, not yesterday. Some day ago, I generated one huge dataset, just images, okay? And in that images, each file is like 6 or 7 kilobytes, okay? Imagine, it's just RGB file, very small size, and each of them is just 7 kilobytes. It's just a text written on very small image, okay? It's like 64 to 32, like it fits only one or 3 or 2 words, like that. And I generated such images of like total 600,000, okay? And now I said, okay, I have no memory in my computer, so I need to move it, okay? And I just grab it and move to my USB, and it's copying. And imagine, it's a USB, right? It's USB. It is generation 3.2, and you need to imagine what is the bottleneck coming between here. Look, computer has own SSD, but the problem is that it is moving from this SSD to the hardware really efficiently, yes, per file. But I mean, if file is very huge, it can move it very efficiently. But my files are very small, like 7 kilobytes. It means, like, you know, it's doing a lot of going forward and backward and forward and backward. So it's estimated to take 15 hours. That's bad. 14 hours. If like another approach, maybe, you know, if I just zip all files as one and move it, maybe that will work. Let me to stop copying, because doing like that is not efficient. Compress. And yesterday I figured out that we need a Verilog is a language, okay? It's not difficult language. It is just low level language, low level language, and we have a simulator. The placement of FPGA, okay? So is it updating or no? It's updating, right? Okay. You can see it, okay. Cool. So Verilog is low level language, and you can install Verilog language on your computer. In my case, I just did pre-install Verilog. And then we can use simulator to execute the Verilog. I'm very curious about, we doing FPGA. Yep, we had. Oh, we are now studying FPGA. I really want to do, but do you also doing that one? Blink. So simulate to execute the Verilog code. So there is simulator which we can use. So what was the name? It's called. Just a moment. It is GTK Wave. So it's open source. It will just show how through the graph. I only know VHDL. To me, it was the hardest class because professor never gave examples. Good. It's good that you studied that FPGA. So, if in order to use FPGA, I really wanted to buy FPGA from from the second hand, assuming that it will be cheap. However, buying from second hand is not a good idea, especially if we want to work with latest chips, because who is selling FPGA in second hand market? People who don't need a FPGA, right? And what kind of FPGA people don't need? FPGA which are outdated, or which clock speed is very, very low compared to the recent one. And for example, their FPGA may be produced in 5 years ago or 2 years ago, and that's already outdated. So we need the latest, efficient, best FPGA. And typical cost for FPGA, it is 200 USD. So we can definitely buy it. I really want to invest on that. It was what? Exynox? No. How was the name? Exynox? No. Helion? Exilions? Something like that. I just took a note. Give me some time to check it. So if Exilion. No, I don't know. It's not here. So the cost was something like this. Yeah, Healings. Yeah. Healings something, okay? But it was latest one. Yeah, Vivido. Vivado. I think that one. Okay. What is the cost? What is the cost? Cost. Not here, not here, not here. Products, maybe. Embedded ecosystem, no. Not here. Not here, not here. You know, I found a very good search engine, you know, compared to this one. It is Brave. No, Brave is better. I found Brave really, really recent and fresh compared to DuckDuckGo. Oh my god, it looks expensive. Okay, anyway, it's not it's supplementary. It's not important thing what we should do now. Focus on. So there is a FPGA, and my budget is like 200,000. We can buy, but it turns out like we can decide which FPGA suits very best for our use case is based on what kind of Verilog code we will write and which one we will study. So who knows how actually the, let's say, GPU works. Just give me some time to remove some 1 gigs of memory. If I remove 1 gig of memory, and then we can work very, very, very like safe. So my screen will not freeze. Okay, it's moving. It's moving. So as I told you before, I have a very like I had a data set of very small sizes, and I just compress whole as one zip file, and I am moving now zip file, and now it is moving really fast. So it will take less than a minute. Okay, it's moving. Yep. Okay, good. I moved it. So now I can just delete. Yep. And now I need to clean my trash bin. Trash bin. How to clean trash bin in computer? If we want to clean trash bin, then we need to go to setting, and then we need to go to trash. Okay, it's calculating. Oh my god. I'm very sorry about my computer, guys. I need to really update my computer because size, memory size. Guys, give me some time. Guys. Okay. I found one very big file I can delete, so that we will kind of have 6 gigs of memory. Are you trying to do embedded systems? Yes. For each assignment in my VHDL class, we had to create different CPU like components. I think we wrote JK flip-flop circuit for the registers, for example. Very interesting. Okay, we have 4 viewers, guys. Good. I am still cleaning my storage, so you can see my storage. Do you want to see my storage? It's just full, you know. We just have maybe less than 1 gig memory, so you can see it, right? Oh no, it's freezed. My screen is freezed. You cannot see it. I'm trying to fix it. It will just take more than a second. Okay, it's 2 minutes. 2 minutes. Today I have a dream. I don't know. I was sleeping. I had a dream, and in my dream, I was an engineer, and we were in a war, fighting. Yeah, Vim is showing, but I actually was trying to show my storage, and it's not showing. It freezed. So you can see it now. Okay. So this is our storage, and that's a big problem in Mac OS. The limitation of storage, very small. So in my dream, I was an engineer who was building a car, you know, to escape from a war zone, or to save a life of a prince, of life of a princess. Very interesting. And in the end, I did build a car, and I just got out of the war somehow. I mean, because I built a car, I played for both players somehow. Like, I was building a car and nobody touched me. Actually, I was helping one person, and then that person get caught by the enemy, and then enemy didn't touch me, and then I just finished my car, and then I called that caught guy, and then he also escaped. I also escaped. Something like this. Very crazy story. Okay, my file is moved, so I can now delete my file, and now we should have pretty good storage to continue our stream. So let me to update my storage. It's calculating. Okay, calculating. Let me to update properties, restart capture. Now it should work. Yep, it's working. So I know it didn't change, the number didn't change for yet, because it's calculating again, and it seems that it's already full, so it's taking some time. So you can check if my computer freeze, we can definitely check why it's freezing. Like, if I activate, let's say, htop, and it will move, right? It will move dynamically, and at the point when it doesn't move dynamically, it means that it freezed. Okay, we will be very, very straight in this. So I want to reduce the size. Okay. Oh. Okay. Let's continue. So FPGA for 200,000. Qualcomm seems to die. CPU stuff. Rise of Japan. And now it is, you know, now what's 2025? Memory card dominance are Samsung, SK, Hinox, Synox, something this kind of fancy word, okay? Synox, Samsung, Synox, etc. So I live in Korea, so what we can do, guys, is that like if we build a chip or if we build a design, and I will go just maybe I need to go to Taiwan, or it's very close for me, you know, to go to Taiwan to fly, and tickets are not that expensive. So we can go and fly Taiwan and talk with TMC, Taiwan microcontroller, TMCS. What was the abbreviation? So that's big famous company which produce the same chip for like which fabricate a chip for people. So we can somehow negotiate with them, or we can talk with Korean companies, you know. And it's the same is happening with these rebellions, you know. Rebellions. It is Korean startup which produce NPU chips. So I wrote it here. So these rebellions, they got funding, and they was established in 2020, founded, and then they produce NPU chips, and mostly their manufacturer are from Korea, so we can kind of compare with them. Yes, I am not a hardware engineer. I don't have a degree on hardware engineer, but I'm very curious about how it will work. And one guy told me that any hardware problem is actually a software problem. And with that spirit that we can definitely dive in, and if we don't understand, we can ask from internet or from the GPT or etc. and just keep going. So where to start? So I installed Verilog. We can write on Verilog. Verilog is similar to Python, let's say 90% similar. Then we have Verilog, we have simulator. Yes, we don't have FPGA to actually check everything. And then simulator. So let me to first make it super clear what is required if we have a let's say we have a hardware, okay? We have already hardware, and what we need in order to able to use that hardware in, let's say, in deep learning, okay? So first we have deep learning stack, right? Deep learning framework. So it is okay, it's freeze again. So we have deep learning framework, okay? So it is, you know, my old computer took so long to do the simulation. Oh, really? Okay, in deep learning framework, so it's what? PyTorch. What else? TensorFlow, etc. And if we write on that PyTorch or TensorFlow, what it does, it asks from like let's say we have NVIDIA, right? But let's say we have NVIDIA, then this PyTorch code or TensorFlow code actually will go and make API requests for CUDA. So request to the CUDA. CUDA is also a framework. So we are in user space. It's also in user space. Then from CUDA, we go to runtime, if I don't mistake. Runtime module. Let's say runtime module. It is user space or kernel space. So what does runtime module do? Runtime module, first of all, runtime module is scheduler. It is memory manager or memory allocator. It's good name, right? Allocator. Scheduler, memory allocator. And from this runtime, it talks to driver. GPU driver. Driver is a kernel space. And driver sits on the target computer, okay? So OS specific. And I see about Vulkan, right? Vulkan. I hear about this word Vulkan, right? Vulkan, which is turns out a cross-platform driver, GPU driver for Windows, for macOS, for Linux. So it is driver. So we have a driver. So runtime module communicates with driver. And driver, what it does is that will talk to whom? Option 1 is just hardware. Option 2 is something in middle. What is that? Do you know, guys? So, okay. Option A, hardware. Option B, firmware. Option C, let's say another CUDA. So it is what? It's firmware. And then from firmware, only from firmware, we can talk to hardware. So firmware is where? In GPU device, in GPU hardware. Hardware is also in GPU hardware. So driver is on computer, runtime module is on computer, CUDA is on a computer, user space, but runtime module, it should be user space because it only activates when user requests it. But it's not a strong reason behind it. There is no strong reason behind it. Okay, and if in that case, if we have our, let's say, what is the name of our chip? Let's say we have our chip hardware. So then we need to build, it means we need to build this cluster. It means we need to build hardware. Okay. Hardware we can fabricate from a local company or from the Taiwan. Second, firmware. We need to write firmware. Writing firmware. In what language? How to write? I don't know. If we write in Verilog the hardware and then in firmware, maybe some kind of, definitely maybe C, because C is very low level. And then from firmware, we need to go up to a GPU driver. Driver is specific for each operating system. And then it should be compatible with our with our firmware. And then we need the runtime module. Yeah, runtime module to how we will manage our resources, how we will allocate our resources. how to allocate the cores, right? So in GPU we have a GPU cores. How to allocate our cores in our, let's say, NPU or GPU. We have runtime module, and then we need a library, kind of CUDA library, CUDA-like library. So this, I think this runtime module is a person who converts this CUDA low-level code. Okay, no, CUDA makes a thing. CUDA takes our Python code and converts to the CUDA code, and CUDA will just map to runtime. So runtime module will make instructions and send to GPU, and from GPU to firmware, and in firmware, maybe in some kind of VRAM, we will store all that instructions, and then we will execute in hardware. That's clear. And now let's look to the rebellions, what they are doing. Rebellion. Not AMD, just wait. We don't need AMD. We need. So they have their SDK. You can see it, right? So model preparation. So it's all what we know. And then compiler. Yes, compiler. So they have their own compiler. They take this code and convert it to the compiler. So it means when we run this code, it means this torch module, if our torch Python code will convert it, no, actually it will not convert, maybe it will request this RBLN compiler API, and then it will compile based on two things, RBLN IR Triton. So Triton is used for compilation. Triton. And then we have a runtime. Yes, runtime. And then it is backup with a driver and profiler. Profiler. Triton. Let me check about Triton. It's from OpenAI. Triton, open source GPU programming for neural networks. Oh, interesting. Vector addition. Triton. Wait, 1000 gigabytes per second. Where? What is the hardware? So Triton is alternative to the CUDA. Guys, do you want to spend time on this? Tips for hacking. Many bug fixes. Performance improvement. Okay, it's support on Linux. GPU. CPUs are not developed. AMD. Okay, it's active. See, 20 minutes ago, it's working. You know, like guys are working on it. It's not our topic of today. So anyway, we understood. So it means this RBLN talks to the Triton or uses Triton. Compile API and then runtime API, and it serve VLLM RBLN. RBLN is means rebellions. Okay, rebellions is startup. What is this? Universal Chiplet Interconnect Express. Universal. It is Universal Chiplet Interconnect Express. Die to die interconnect. It's how they will design this. They will construct this whole chip. I think this is 1 core, 2 core, 3 cores, 4, 5. IO means bus to connect, to talk. Capacity. I really like how they compare with H200. No, we need to read blogs, white papers, white paper. Okay. Advanced AI system on chip. System on chip means everything, all components of chip is inside one chiplet. me to connect my computer to the power. Okay, we have a power. So system on chip means the same chip as in what in the same strategy as what Apple is doing. Everything is one chip. UCIe advanced chiplet. So it is common open source, no, not open source, let's say architecture, which is famous. Maybe it is what Apple also using. Do you want to go to Apple? Let's go to Apple. Apple M1 Wiki. ARM based, so they are talking openly. It's ARM. And it turns out, guys, that in this hardware, like let's take the NVIDIA GPU, they have an operating system inside the hardware. They locate the hardware as a operating system. It will be very small operating system, but it will be operating system, and it will work to control memory, or to auto control itself, or to terminate itself automatically based on the temperature, based on some kind of thermal stuff, and it has a sensor of temperature, measurement of temperature, and that is kind of logics applied to the hardware inside the to the actual hardware of GPU. That's cool. Nope, no. UCI. UCIe. You mean the rebellion is risk 5 base, right? You mean these guys? You mean these guys work on this rebellion quad on risk? Maybe yes, I also think so. Like I see a lot of startups using this risk. To meet extreme compute and memory demands of serving frontier LLMs at massive scale for hyperscalers, AI, data centers, and enterprise. So fancy. So this is their chip. Why is it divided in these windows? Okay, Korea 2517. I don't know what is that. It features unified hardware software stack that maximizes utilization and delivers exceptional performance per watt across both compute bound prefields and memory bound decoding phases. The chiplet based design enables hyperscaler scalability without compromising latency and coherence. Yes, I agree with latency. If everything is unified in one stack, it makes sense. But they're talking about exceptional performance per watt. Yeah, I agree, and I agree with that. And people talk about NPU because NPU are power efficient, and they are only focused on this AI stack, on making AI, right? And it consumes less watt, therefore. But actually, exceptionally very efficient per watt. is, I don't know how to compare yet, because I'm not that much understand about what. So let's say my air conditioner, if I turn my air conditioner for one day, for 24 hours, then how much energy will it consume? And we can like compare with that. Like it is baseline, okay? Air conditioner is like our baseline. Air conditioner or my fridge. I can check my fridge. Just give me some time. 23 kilowatt per month. 23 kilowatt per month. Okay, my fridge generates 23 kilobytes per month. No, not kilobytes, kilowatts. What? Not kilobytes, kilowatt. Okay, this chiplet. DMA, I don't know what is it. CMD Proc Synchronization Manager, TBM3E, and we have this here UCIEA. Okay. This UCIEA is like a transport, like bus interconnect. So it's like universal, right? Universal chiplet interconnect express. It is a bus between chiplets. It is a bus between the chiplets. So you can see this connect, this talks with this chiplet 0, and it talks to this chiplet 1, and it talks to chiplet 2, it talks to chiplet 3. Good. So it's just a bus, clear. And they make 4 of them. And they are saying that we can make 6 of them. Or they are saying like we can make it 10 of them. Or just 1 of them. Or just 2 of them. Or 7 of them. Here is PCIe. What is an PCIe? UCIe means universal chiplet interconnect, right? Here P, chiplet interconnect express. What is P then? P. PCIe. Peripheral component interconnect. Okay, it's just it's the same thing as UCI then, but peripheral means, where is the peripheral? Let's say if I take a rectangle, what is the peripheral of rectangle? It is the edges. It is edges, okay? It's just edges. In that case, peripheral means edge, and then it is a interconnect also. It's also a bus. Just relating to or situated on the edge of something. I know that word because when I was taking some preparing for GRE, I get this word peripheral, and then I just remembered. Very good word. M1 no. Okay. 32 megabytes of L2 shared memory. 32 megabytes. Isn't it a very big number? No? 32 kilobytes. 32 megabytes. Let's compare in RTX 3090 L1, L2 cache size and registers. L2 cache of 6 megabytes, and it has 64 registers per thread and per block. Thread means core. Are you talking about core? Let's look here. Okay, they have also PCI here. PCI Express 4.0 and then L2 cache. Okay. L2 cache is lives between these blocks 1, 2, 3, 4, 5, 6, 7. Between these 7 blocks. So all of them are using this L2 cache. They can have access. And they have a L1 cache, which is, I believe, should be here. For example, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. In one block, we have 12 small cores, and each core has their own L1 cache, and each of them can also access L2 cache if they want. NVLink. I don't know, NVLink. Okay. Custom die-to-die protocol. Protocol die-to-die. It's kind of communication protocol. Okay. Okay. What is their advantage? What is their advantage? Okay, they have a core and their L2 is very big, 32 megabytes. And PCI is generation 5. I mean, PCIe is just, I think, universal, like standard, which every company should use. And this interconnect is also. And where we can kind of innovate. Maybe we can innovate in terms of we can change the memory size. We can increase the number of cores or decrease the number of cores. Or we can change the number of neurons per block. A number of these cores per block. Okay, let's see. In this neural core, they have L1 of 4 megabytes. 4 megabytes it's very big, isn't it? Huh? For me, it seems like very big. But I see that people like usually people implement like not people like let's say some companies implement L1 caches like in kilobytes, but they have megabytes. Vector processor, tensor processor, 14.8. What is TFC? TFS. TFS. Task manager. Load store. Vector processor. This is super clear image, okay? This is super clear image. I need to save to downloads, okay? Let's say, guys, let's say we will build this one, exactly this one. Oh, you cannot see my screen. Again, please. Okay. This is what we will build, okay? Let's say this is what we will build. And what we need to build. Let's say we will just use this first chiplet 0 to build for simulation. I know it is very ambiguous plan, guys. It's ambiguous plan. But we'll do it together, guys. And Blink recommends that our subscriber, he says that it is risk-based, in his opinion. Risk-based. I watched the George Hot's video. He made it 4 years ago. That he used risk to build a chip. But for him, it took 8 hours, you know. For him, it took 8 hours. Okay, let's dive in. Let's dive in. Let's dive in. Risk 5. $2019 is it fine? It should be fine. How to write Rox 16-bit. Okay, now we have a reference to check. (32-bit risk 5 ISA based process Verilog. Yeah, I'm talking about this program. GTK Wave. It is a simulator. Which one we can use? Cool, guys. Cool. Okay, guys, we will continue based on this one. But the point is that it's saying 32-bit RISC-V processor. if we believe that this is RISC 5 or RISC architecture, then it should be very big, right? I mean, 32 bits means very small. I mean, 32 bits means what? What does it mean? What does it respond to? 32 bits means a memory capacity of 32. MIT, I love MIT. Okay. I have already set up this one. This one is what? Add. Or maybe it is instructions. Can you see it? I think no, you cannot see it. What about now? Better? Okay. Okay, 32 bit of memory address. Address for what? Address for instructions, maybe to store. Or no. We have registers. Registers. What does register do? Register takes the instruction and put to an address, and take from address and give to the CPU. Okay, we have 128. Signed integer value. Okay, I have confusion. To be honest, I have confusion about this signed integer. Signed means some kind of crypto encoder or crypto stuff is given on that number. Signed. What was that? Signed. So when I check the Telegram protocol to communicate, they use a term signed also. Let me to show in practice. Let me to show. You will have a very, very clear idea of what I am talking about. So let's say I have Python, and then I see 2 bytes. No, not here. Yeah. If I remove signed, it's different number. If it's signed, it's different number. So there is something in signed, you know. Okay, each base integer instruction set. Instruction set. It's set of instructions by width of integer registers and corresponding size of address space. Right. Each base integer instruction set is characterized by what? Widths of integer registers What is the length of registers? And size of address space. Size means the length or number. And by the number of integer registers. What? By and by? Okay, width of integer registers and integer registers and number of integer registers. So it means if I have 32 bits and if my model is very fast, if I have a 32 bits and if my instruction sets are less, not that many, if I have few instructions, then 32 bits is fine. I mean, 16-bit is also fine, or 8-bit is also fine. 8-bit I didn't see 8-bit, but I saw a 16-bit. 64-bit is very big, I think. And then we have a 128-bit. Okay, let's go to chapter 2. What did George use? 32? Yeah, it's using 32. It's using 32. Our RISC-V 32 UI. So in this one, 4-core instruction format, we have R type. It includes funct7, RC2, RC1, funct2, RZ, opcode, and so this is just binaries, okay? Just binaries, and it's saying from 0 to 6 it is opcode, from 7 to 11 it is this RD binary, and from 12 to 14 it is funct3 binary, and from 15 to 19 it is another binary. And you can see all of them has an opcode, and RD is not on every one, not in all one, but you see the size of opcode is same in all instruction formats, and the size of the second one is also same. So it means that reading by this one and this one, it gives us a pretty good sense of what type it belongs to. Okay, RD means destination. RC means a source. Okay, source, destination. It means what kind of operation to do, where is the destination, what is the source, what is the source, what is the function, what is the function. Gonna sleep. Very interesting topic. Okay, have a good sleep. Good sleep, and yeah, just go sleep. We will continue because it is morning for us, 8 a.m. Wait. Immediate variance. Okay, that's enough for me for now. So let's go with this code, okay? So we have instructions, okay? iVerilog we installed, GTK wave I have installed. Getting started. This is example of how you may give instructions on setting up your project locally, okay? To get locally, copy up and run the following simple examples. Okay, let's copy it up. So Okay, 1 a.m. You need sleep. It's the perfect time when it's actually time when you should be sleeping. You know, you should be dreaming of something. So okay, you can see my screen, right? And then we are okay in the main place, but we need to go to fun and then our chip, and here git clone. Okay, let's go. Okay, we cloned it, and then look, we must initialize instruction memory with desired sequence of instructions that we want to execute. By default, 8 instructions are included that will execute in the particular sequence of initialization. Okay, 8 instructions are initialized. Okay. They are given by default. Initializing the register file. In order to implement instructions, we must have values in the register to act upon. Those values can be initialized in the register file. By default, each register is initialized to have a value the same as the register number 1. For example, register 14 will have value 13. What? For example, 14. Okay, yeah. Register number -1. Each register is initialized to have a value the same as the register number -1. Once the above initialization have been done as desired, compile the file. Processor V using iverilog using the following command. Compilation. Reset. Okay, it's lu control database instruction fetch unit processor register file images. I mean, images is fine. Images I understand it. This one I understand. Which command? Processor TB. Where is the processor TB? Processor TB. Okay, processor TB is in a processor. We go to processor and then we run this one. Let's try it. Let's try it. Touch bank output wave. This is what we are having. So I compiled the Verilog and then we executed the Verilog and then we use that Verilog, I mean a compiled file, this output wave VCD, and then we are using this GTK wave software to run. However, we don't see anything here. So it's time, okay. Oop. Okay, I understand. I understand now. So this is our clock. Clock equal to 0. What does it do? What does it do then? Instruction code, clock. For guys who don't understand about very low level about clock, so clock is one cycle. For example, let's say this iPhone. Let's say this iPhone has 5 gigahertz, 5 gigahertz or something like that. I will prove. Let's say iPhone 13 chip. A50. Okay. Three dot 24 gigahertz, 2.101 gigahertz means in 1 second they have 2 giga clock cycles in 1 second. Do you get it right? So giga. So how many zeros in giga? Giga. Not gigabyte. I mean just giga. 10/9. 10/9. Billion. Okay, billion. It means 2 billions clock. 2 billions clock cycles. But all of them has a clock. Interesting. I was thinking that clock is only we have only one clock for one chip, but there are many clocks. So what numbers are changing here? Okay, here's the clock done. New clock starting. New. Okay, here new assignment, new instruction code, new is assigned. Here is new number, new number, new number. ALU control is 4 4 20 4 4 F F F 8 18 19. Okay, these are changing. 8 18 9 19 8 9 12 13. What's the number? Why data? Okay, anyways, this is a visualization graph. Okay, the syntax is like this: initial began and dump file, write a variable, and then end. Initial began and then reset 0. What is this? I don't know. Reset 50 and clock forever and module stimulus. This is just the result, just logs. I mean, this output wave VCD is just logs of our execution. Instruction code, ALU control, reg. IFU, what's IFU? Processor. Clock reset 0. Okay, ALU module is what? It takes 2 operands of size 32 bits and 4-bit ALU control ID. ALU means arithmetic logic unit. Okay, we have all of this implementation. It's very good. We don't need to write this one. Bitwise AND, bitwise OR, and extract, set, etc., etc. Shift left logical, shift right logical, multiply, bitwise OR. Guys, do you know all of this? How does this all work? Feel free to write on chat if you don't know, if you want to, if you have a some idea or curiosity, right? So shift in Python, I know how to implement shift, multiply, XOR I know, or and I know, subtract. Add subtraction is I think everyone knows. everyone who can use internet, I think they know add and subtraction. Set on less than. Set on less than. Set on less than. I don't know. Maybe if function. Okay. LU. Okay, if it is 0000, if the LU control, then we are doing this one, this one, this one, this one. 0, 1, 2, 3, 4. Super clear, right? Super clear. But who did this one? I mean, who will actually implement this one? It's not that low level. There is also abstraction layer here. Wait. Okay, it's not importing anything from anywhere. I think it's Verilog. It is job of Verilog to execute that low level. Vim LU and then what? And I know LU, but what about rig file? Read 2 registers and write on to 1 register. Okay, RISC-V has 32 registers. Each of them is 32 bits. Ah, yeah. We can map it like, we have x86-64 architecture, right? And here we have 32. So, okay, 32 registers. It's decent number. Register file will always output the value corresponding to read register number. It's independent of any other signal. It's very similar to Python. Okay, register is fine. IFU. What is IFU? Instruction fetch unit. Instruction fetch unit. So it means it will get the instruction. Has a clock and reset pins as input and 32-bit instruction code as output. Instruction fetch will get the instruction and return it as output. Okay. It inputs clock and pins and output the instruction. Okay, we import this instruction memory, I think, And then we define our this module, let's say a class, and input is just clock and reset, and output is 0 to 31 means 32 instruction code, and it means based on clock can be 0 or 1, and reset means 0 or 1, and then it means we have very limited instruction codes. Okay, we will use this instruction memory, initialization instruction memory. It's very similar to C, and you have a semicolon, and here's the number of the name of the class, type of the class, let's say, and we call instruction memory. We include, how you define this instruction code? Wait, PC. Where is PC? PC is this one. Okay, we pass 0, all 0, 32 bit of 0 stuff, and then reset. Reset is given. Instruction code, it's not given. Always. At what? Pause H, I don't know. Pause H, reset, begin. If reset is 1, PC equal to 0. Else PC equal to 4. Maybe always when they changes, check. For each clock we include 4. And. So maybe maybe when you use this one, you need to output you need to include the arguments, and you should also include the argument for output, I think. And how you return it. Automatically it will return, I think. Okay, instruction memory. Okay, let's say. So what does it do? Is that it takes the clock and reset and gives us instruction code, and it uses also a counter. And if you use reset equal to 1, it will be true, and it will reset the counter to be 0. Exactly like this. And then let's check the instruction memory. Instruction memory takes in 2 input, 32 program counter, yes, and 1 bit reset. Yeah, we got it, guys. We discovered that it input 2 things, and also we also give the instruction code as an output. We ask also give me output. Like we have a, let's say we have a plate, and you make a spaghetti, and I just bring my plate to you as a function. Please give me food, and you put your food to the output and return, and I will return it by myself. It's something like that. So it depends on program counter. It means first it will be 0, 1 clock cycle, 4. 4 means 4 bytes will be added, and 4 bytes. Each 4 bytes means, actually, why 4 bytes? They put 4. In code they put 4. 0 0 0 0 0 0 plus 4. Can I do like that? Right. Guys, if my screen freezes and if I don't notice, please tell me. I will refresh my OBS capturing. You can see it from this right side, okay? Right side. It is dynamically moving, right? This, for example, my 0 core is working very, 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 very high. This is not working. They are moving. If they stop moving, it means something wrong, okay? In that case, I will go and check my computer, because my computer today is very, very laggy and slow. And for new guys who join the stream, don't hesitate to ask questions or ask what you don't get, or ask what we are doing. I mean, do you want me to explain it again what we are doing? So let's say we have a binary, right? It means what? It means binary. How we used to write binary? 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. 23, 24, 25, 26, 27, 28, 29, 30, 31, 32. So this is binary. Okay? And we plus 4. Actually, a counter, how I study it, is that it should add only one. Only one. Only one. It means, what I mean is that 0, B, 0, 0, 0, 0, 0, 0, something, 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 and 1. And then it should be 10. And then 11. And then 100. It should scale up like that. Okay, anyway. So that's about... So just take it as an abstraction, okay? It's just black box for now, okay? We register. Look, instruction code is assigned based on the program counter, and program counter, it depends on clock. Clock depends on what? How each operation is executed. So all is solid, valid, powerful. Instruction code, okay, instruction code is combination. Look, memory PC plus 3, memory PC plus 2. Look. We can do plus 3, we can do plus 2, we can do plus 1, and we can put itself also. If reset, we will reset everything to 0. If it is reset equal to the 1, we will make an instruction which will reset other thing. H00 64 03 33. No, you cannot see it, right? If you have a memory object, where is a memory object? Where it comes from? Register array of 8 numbers, right? No, register 7 of memory objects which has 32-bit length. Okay, here we have instructions: add, sub, mul, xor, sll, srl, and then or. I mean, one instruction, two instructions, three instructions, 4, 5, 6, 7, 8. We have only 8 instructions, right? We have only 8 instructions. That's how instruction is fetched. And then what is data path? Data path. We use LU. As you remember, LU is arithmetic logic unit. Reg file is that we take 2 registers and assign to 1 register. In order to use data path, we need a 4-bit register 1, 4-bit of register 2, and register where we need to write, destination register, and then what kind of control. Then this is a brain, no? Database is a brain, our brain. Look, we take first register, second register. I mean, we tell the source 1, source 2, and then destination and the control. And we have the register write, clock, reset, 0 flag. I don't know about wire. What is the wire does? Yes, 32 bits, 32 bits, 32 bits. File. Reg file module. Okay, it imports a reg file. So in reg file, as we know, it takes 1, 2. Then there is a LU control. LU control, LU module gets data, control, write data. And write data is, what does the reg file do? Okay, reg file do in abstraction, it takes 2 source and write to the sort this to the destination. So they have this reg file, input, output, and then input, okay? So this output, so data pass, okay, it goes and says reg file module. It calls the reg file module and input, output. This is output, okay? Read data 1, read data 2, output, input, and then we give the input. So reg data 1, reg data 2, it comes from the reg file module, and we give it to the LU module, and then we pass also LU control and write data and 0 flag. So in LU, if I don't mistake, the write data is output and the 0 flag is also output. Yeah, 0 flag is output, LU result is output. Which means data path is the main logic which will connect the arithmetic unit instructions and the registers. Then what left? Data path, instruction, processor. And now let's go to the processor. the head. We have a clock and reset. And we wire. Wire means initialize. Oh, we didn't check the control. Let's check the control. In control, we have input of 0 to 6 means 7-bit, 3-bit opcode. There's only one R type instruction. Where's another instruction? And why it's changed, guys? Why it's not consistent? No, guys. One. Okay, enough. And it turns out they have only one opcode of one type. We end case and we end this if. I don't like when this is inconsistent. Let's go and let's add. Okay, if we have, okay, how do we use this syntax? Begin if. In Python we have elif. Okay, it's not addressing. Okay, I see. Else if. Done. See? This is the logic. Oh, no, you are not seeing my screen. Now. It turns out they have only one instruction. It's very sad that they have only one instruction. R time instruction. Vim processor TB. Look, in processor we have a test processor where we pass 0, reset, clock, and it creates this file and calls a stimulus, call itself, and then reset equal to 1 and then number 50. Okay, 300 means hashtag 300 means hashtag 300 seconds, 300 iterations, or 300 what? 300 iterations and finish. I like number 9. Let's go. What will you do? 900. Okay, guys, we discovered. We found. Or also known as counter. Maybe 50 is like that. Reset initial begin dump file. I don't know. Dump file, dump variable. What is wire? It is a module name. Okay, then what does wire module do? I don't know. Or is it initialization? Maybe. Oh, today it's October 8th. Good. When I call gen compile, output wave is overwritten. Yes. If I use iVerilog, gen compiled is overwritten. Yes. Do you want to see the compiled one? This is beautiful, low-level compiled version of Verilog language, and here it is. Okay, my computer freezed again. Okay, it turns out when I do some kind of very graphically difficult action, it will freeze. I'm very upset because why they didn't implement all the opcodes? Actually, my roommate is sleeping now, so we should speak a little bit low. Okay, now let's go and read the risk. So we do believe that it is a risk, but I don't know. I don't have a good, clear, not solid proof of that it is a risk. Maybe I need to go and meet with this CEO. explore docs. Okay. Docs are here. Developer boards. Do you have boards? Really? Can you give me for free? Nah, nobody give me for free. ISBUJ. Wait. So a lot of information in one sentence. Similarly, okay, the only difference between U and J formats is that 12-bit immediate is shifted left by 12 bits. A 20-bit lifted by U and J. Look, here we are only using from 12 to 32. So we have a padding of 000 until 12. Maybe. Or similar stuff. Okay, why I need this kind of ops? No, it's not ops. It says what? Instructions. R type, I type. Okay, I type. Okay. Okay, R, I, S type. And then U type. Let me to look. MB type. Okay. Okay, output wave is different. Yes, process TB is different. Really? What's different? I just changed some. I add some comments. Yes, yes, yes. Sure, 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 sure. Sure, definitely, definitely. So guys, here I understand we have instructions. We are in very low level. Okay. I mean, we are in the lowest level of Verilog. There are also lower level of the of our stack, but I am in between. And but it is very low if we compare it to Python. You know, Python and this one has here a gap. Python is inter OS, but this one, the Verilog, is actually the very low level, lower than C. Okay. Let's read this one. Yeah, I feel a bit sleepy, so what we will do is now is that I need to do push up. Okay, I found very good tactics to at work that every 1 hour you need to do push up. I will do push up. Just give me some time. Push up. Okay, I am back. I am back. So we have this one, okay? No, you need to be honest. There is only one instruction type. R type and I type are the same, except this im 11 to 0. And then S type and B type are Looks same. They look same, right? They look a bit same. Here two, here two, here one. But I don't know exactly what is that. We need to study. We need to study here. Immediate. C immediate, B immediate. We need to build an immediate stuff. The fancy. This is all instructions. All instructions. And they belong to one of the 8. One of these, or it belongs to R type or C type, B, U, G. Didn't George implement that? Okay, he's writing here the all opts func3 add sub add slr stu xor and opts. Let's check the code faster. Risk. Oh, we can test it. Twitch core. Okay. It's like Verilog we are using. GNU. What is this? GNU is a compiler. Okay, we need to be fast. I am slow, I know. I need to be fast. If you are this much slow, we will invest maybe like 24 hours or more like now for streaming. We need to be fast. We need to be fast. Robo advisors? What? No. Generate. Because there's this kind of small things which we need to figure out. Look, let's say we have 32 to 32 bytes. 32 by 32. 1000. What is im encoding? Okay, load, store. Okay, we're using Python. We are using Python. Fine. What is ELF file? ELF tools. Is it some kind of low-level thing? Analyze ELF files. ND-WARF debugging information. Okay. This is implemented. Condition is not implemented. And then RAM. RAM means... Can I say RAM is a database? No? It's the end of the module. So what does it do? Top TF CPU. Risk extensions. 4x4 registers. We have 270 10-bit RAM. Need this instead of 19 depth. 1024. Let's make BRAM. So it means bandwidth. 2304-bit wide the bus. If we only use one port in big chips, is also the size of ECC. Use 9-bit Mantissa cherry float. Mantissa. Okay. Wait, the core is this one, right? We have here LU. We have here conditions bigger than BLT BT. No, it's not that. What we mean. No, I cannot find it. F extension, B extension, C extension, etc., etc. RV16. Okay, this is what I mean. This is what I'm looking for. What? one good question is to ask is that what it take to us to build a hardware which will make a perfect, really fast 16 by 16, let's say 16 by 16 matrix, or like 32 matrix to dot product of 32 to 32. How efficient can we build this one? 32 by 32 matrix dot 32 by 32. What is the output? R type, I type, C type, S type, U type. This is a bit confusing. What is confusing? What is IMM? Let's prove this one. Okay. 16 kilobyte means 10 for 24 is what? Is bytes times 8. Hmm. Sixteen thousand 384 kilobits. Address. Okay, standard exception. Where is the K standard extension? K, no K. There's Q. Maybe it's this one. No. 5 years ago and no result. One commit. Pages. Why in pages? Why do you have in what do you have in pages? Okay, now it's time to do some good research. ML accelerator. What's this one? End-to-end risk solution for ML on edge using in-pipe support. Boston, Google. 2008, 2017, 2019. Okay, it's probably done in 2020 maybe. TensorFlow, sparse. Open link. Okay, it is empty. It's empty. Not here. Not here. Not here. What they are saying? Okay, introduction, then what? Okay, you built it, right? No? Okay, basic compiler support. They did a lot of work, okay, and used to implement TensorFlow right operations such as convolution matrix. Okay, they already implemented this one. This is optimization, TensorFlow right source code, cross compiler. What is Spike? Benchmark ML models. All of our works are open source. Okay, awesome. The model are 32 bits floating. Let's check this one. But it's said that this is not open source. I checked this website. No? Look, they use a specific simulator. Spike number 5. Number 5. Search. Rocket chips. Okay, we are building rocket chips, guys. Rocket chips. Developed at UC Berkeley, designed from the ground up to clean the mechanical control, diagnostic and high extensibility. Okay, risk is free and open source and commercially available and open source standards. Okay, very good, very good. L1, L2. And where is the simulator? Where is the simulator? Risk boom. Berkeley out of order. No. We release support for deploying rocket chip to a variety of links, zinc, FPGAs. Okay, good. Silicon prototype acknowledgement. Let's go here. No? Rocket chips. Search. No, it's not here. We are lost in the information, in the float of informations. So rocket information. Nope. That's a floor. No. Instruction set simulator. Okay. Good news. Spike. Simulator. Okay, now we found it. I need K. Awesome. This is the core. This is beauty. This is beautiful. We assume risk environment. Install pass. Okay. Can I run on Mac? On OpenBCD? No, it's not what it's not our operating system. Yum is I think in Ubuntu. In CentOS. C program. So we need to answer how can we continue doing the matrix multiplication or efficiently. So let's read this paper. I know this paper looks a bit old, maybe like 5 years ago. Then okay, let's go from beginning. Over the past few years, researchers have shown that machine learning is the best solution for a variety of mobile applications such as image recognition, speech recognition, natural language processing. Yes, of course, yes, agree. Then, to accelerate the computationally intensive tasks in ML-based applications, the tasks are commonly offloaded to the accelerators. GPU, as we know, it is NVIDIA, AMD hardwares, TSP, distributed. Okay, I don't know what is. I don't know this one. Digital signal processing. Nah, it's okay. It's not DSP. Distributed. We should check it. Digital signal processor. Okay. The digital signal processors or special purpose accelerators like NPUs in mobile system on chips. This heterogeneous. We have heterogeneous and homogeneous approach divides in the task between the host CPU and the accelerator, which requires us to use special instructions. Okay, look, here they are saying that we use NPU, and NPU can only be used as a accelerator to the CPU. Okay, CPU is required anyway. It's like NPU is inside this COS. But in this rebellion, they don't have CPU, as far as I understand. Here it's just core, but anyway, no. Anyway, it should talk to the CPU, right? Anyway, it talks to CPU. Yes, they're right. I'm wrong. It talks to CPU. It should talk to CPU. Depending on this application, this may trigger frequent host accelerator communication. In this solution, the whole ML task is partitioned into 3 main steps. Whole ML task is partitioned. Okay. Pre-processing the input data to make the consumable by the accelerator, running part of the application, On accelerator input data and post-processing the result is generated by accelerator. This time spent on pre-processing and post-processing operations and the time required to transfer data between the processor and the accelerator makes this approach suitable only for applications that have large amount of computations that can be offloaded to accelerator. Okay, large amount of computations. Applications with a small amount of computation can be offloaded to the accelerator cannot sufficiently amortize. Wow, amortize the communication overhead. Moreover, applications that involve frequent data or control exchange between CPU and accelerator end up severely underutilizing the accelerator and may not see any benefit of loading work. Okay, makes sense. There might be no benefit to upload to the accelerator if the computation, if the computation is not expensive, in terms of that it will be huge computation. If it is huge, then it's good to upload. If it's not, it should be stay in CPU. Otherwise, it will be just overhead. That's clear. So they took this architecture and extended like audio and video processing, video and facial recognition, computer vision and deep learning on processor. Today nearly mobile inference Android phones run on CPU rather than uploading to co-processor or accelerator. Yes, on Android it's like that. CPU what is CIMD? Single instruction, multiple data. Okay. Single instruction, multiple data. Okay, guys, take a note. Okay. Single instruction. Multiple data. As a first step to explore the ideas, we developed the software stack for supporting custom machine learning instructions. Okay, they built custom instructions. We had the instructions, right? The opcode and then ALU, and they built a custom of that. And they use RISC because open source. And we also believe that this startup also using RISC somehow. Where is that? Okay. We developed the required inline assembly support and built the runtime environment to map tensor-flight kernel operations such as convolution, matrix multiplication to low level. Okay, they put a convolution operation to the low level. This RISC instruction set execution, maybe ICA execution. Okay, low level execution. At the next step, we plan to take the software stack and prepare end-to-end solution to accelerate the execution of the ML-based application in the main processor. We will develop RISC v5 based in pipeline ML processing unit called RV MLPU to accelerate DNN inference task on the main processor to avoid overhead of communicating with the external accelerator. Okay. Okay, they use this ROSC v5 open source because it's open source. Okay, yes. C inline assembly. They modified Spike and instruction set simulator to support the extended instructions. They use a Spike also, and then because they added the instructions and they modified the Spike also. Function verification, they use Spike to function verification and benchmarking ML models. All our work has been open sourced. They evaluate the performance of DesNet, MNESNet, Inception, ResNet, MobileNet. Almost YOLO tiny also. Speech encoder and decoder. Awesome. It's big work. These are commonly used ML inference models and deployed on mobile devices. We cover a wide range of applications using these benchmark models. The model are 32-bit 14 points and hosted on TensorFlow website. Okay, okay. It's clear that they use from TensorFlow Lite, and they are also already converted to TensorFlow Lite, and they utilize it. And 32-bit 14 point. 32-bit 14 point means torch dot float 32. Maybe they move it to 16 or maybe even 8. We use the executed instruction count as a metric to compare the modified RISC v ISA with ARM v8A with Neon advanced with Neon. What is Neon? Advanced CMD extensions. Wait. They have this architecture. Okay. They're comparing their RISC architecture with ARM v8A. So Apple M1 and these A series chips are powered by ARM architecture, but it's not exactly this v8A. They have different one. And Neon advanced CMD. Neon. Who is Neon? Neon advanced. I haven't heard about Neon. Just pipeline. Where we are? Here. Okay, God, it's freezed. God, it freezed. Okay, they make a 128-bit register width and 256-bit register. In comparison, we did a 32-bit. Okay, 32-bit. The width of the register. Because they have a prior work 6. We should give me some. My roommate is eating breakfast, but he's not sharing breakfast. You know.
Okay, brother, I will just want to cook eggs for us.
Please cook me 4 for me.
What you did? Shrimp? Just for shrimp for eggs? No, I need enough.
I hope it's not noisy. Look, vector processing unit. Vector processing unit, and here we have a vector processing unit. Seems a bit very similar. Vector load store unit to handle 3 different vector memory accesses. Unit stride load and store, which access a contiguous chunk of memory. Constant stride load and store with access memory addresses, spaces with fixed offset. And then constant stride load and store, which access memory addresses spaced with fixed offset, and scatter and gather memory operations, which use a vector of offsets to allow general access pattern. We plan to open source in near future, and you are giving these links. A bit strange. Case specification, but there is nothing here. And if I go to this link, it is broken. Let's check this one. Hardware performance counter can detect malware. Carbon. Black parrot. Nakhotki, we don't have this kind of thing. Look, there should be implementation of matrix multiplication in RISC. On T RV and this vector. Okay, so they open source it, but it's not available now. There's something happened there. We don't know. But this is what is. What does this graph mean? Sahra Asad, Azad, Makio Sahaya, Leila, Anthony, Suyok, Pete, Vijay, Ajay. I see. Okay, it's already implemented. Very good. Mm-hmm. Do they write in Verilog? No. It seems like they are not writing in Verilog. Let's check the demo. x86-64. It might not work on my case because I don't have that one. This is awesome, guys. It did matrix multiplication as an instruction. Finally. Okay, how to run it? We need Chemo project. Chemo. Not here. Is it here? Okay, very long. This is very long. This is good. Okay, guys, I have eggs. I need to eat eggs. Breakfast time. Wait, it's Chemo. I'm going to Chemo. How to download Chemo? Oh, sorry. Can I run it? Yes, we can run it. Let's go. Why are you taking the food? Give me a little bit. I should also eat yesterday. Why you eat today? Where? Kebab?
Guys, we come back.
I want to update submodule. Couldn't read from remote repository. Permission denied. Why? Okay, let's generate it one that one. Okay, I have some problem with SSH. Not SSH, with this key generation. CH. Recent. Dot pub. Yep, public. Yes, copy it. Okay, copy it. And then I mean, I did already that kind of thing. Okay, it's getting bored. I'm getting bored. Now I need to log into my GitHub, and you will see all my GitHub stuff. That's not good at all. Now I need to go and to my profile, to settings, etc., etc. Maybe working. Maybe working, maybe not. Maybe yes, maybe no. For some reason, it's not working. I mean, it freezes maybe. Or maybe it worked. It worked. It worked, guys. It worked. Awesome. Good, good, good. We have good news. It's in California. Washington, New York. Where is New York? Is New York the site? In the site? No. New York here. Okay, it works. What about make? Does make work? No such file because we need to execute. Cannot execute binary file. Okay, we can run that compiler on macOS, but in order to run, we need to install these modules. So now I'm installing the modules, and then we can replace the compiler on our chip, not on Linux, and then we can hopefully execute. And I need to check the env. He's using this one, but I'm not using that one. will not work. Okay, the same thing is done by this open source which I downloaded. This one, recently. But I am not a Linux. Where is a file configure? Where is this configure comes from? Wait. It should be here. It's not here. Okay, let's sum up what we did today. Okay, risk file. So we have a risk architecture, and it is open source and all people can use it. In addition to that, we have a startup which probably uses this risk file, risk architecture, and we learned that this UCI is a bus, interconnect bus, and this is a peripheral bus, and we have a core. L2 is 32 megabytes, L1 is 4 megabytes. It has vector processor. It supports 14.16 and 14.8 cores, and that's it. And what George Hotz did the stream 4 years ago. I need to watch this again. Yes, or do you want to watch together? I need to watch this again, and I have some bugs, problems with the compiler. Now we should figure out. I should figure out. Then what? Then done, right? Then we just run a small Verilog program, which hasn't implemented all instruction sets. So I will get back soon. Have a good day. Have a good productive day. It is 10 a.m. for me. Oh, 11 a.m. for me. So yeah, have a